In question 10, we've been given the following diagram. They told us that these two lines are parallel to one another. And they also gave us this, QB equals 5 times BC. That's like a very sneaky way of giving you a ratio. So we're going to sort this out quickly before we even look at this question. So with something like this, we want to get all the letters on one side and all the numbers on the other side. So what I'm going to do is I'm going to divide both sides by BC. And after I do that, these BCs are going to cancel with each other. And then this just stays behind, QB over BC. And we just have the 5 left over after the BCs cancel. But I want to kind of write this as 5 over 1 so I can quite clearly see the ratios.
Yeah, that's much better, but...
Okay, so we're going to fill this in on the sketch. So QB is 5, so we're going to do a 5 over there, and BC is 1, so we're going to do a 1 over there. So you must just watch out for these statements in Euclidean geometry. It's a very sneaky way of giving you a ratio of two sides. Okay, now we need the ratio CT over PC. We're going to pretend like we don't have this and basically show the teacher where it comes from. So CT is over here and PC is the long side over there. So I can take the ratios across the parallel lines, bro. The line parallel to one side of triangle. Yes, and this paper is really hitting home on this theorem. We've seen it a lot in this paper. So just a quick reminder, you follow the parallel lines up and then the ratios are the same on the other side of the triangle. So we've got a 1 to 5 ratio that exists there. And we can also do like a big scallop across the whole thing, and 5 plus 1 will give me 6 parts for that ratio. So we can just add in that 6, and with any ratio you get like sort of 3 parts to it. The sort of medium size one, the small size one, and the big one that goes over both of them. So I'll fill that in with both of them. So we can see now CT has 1 part, and then PC has 6 parts. So if we just say CT over PC, it will give us 1 over 6. But there are a few things we have to write down over here. So let's walk through how we're going to write this down. Firstly, I'm going to start by writing this CT over PC, and then I'm going to put an equal sign next to it. And then I'm going to show what ratio this is equal to. CT corresponds to the side BC. So I'm going to put BC on top there. And PC is this huge scallop, and that corresponds to the side QC. So I'm going to put QC at the bottom there. And then my reason for that is line parallel to one side of triangle. That's how I take ratios across parallel lines, is line parallel to one side of triangle. Bear in mind you can also use the proportional intercept theorem. So now we're going to leave this side and we're going to start sorting out this side. So what I do is I leave the smaller side. So BC is going to stay behind. And I'm going to start transforming QC. Now QC is made up of BC and BQ. So I'm going to change QC to QB plus BC. And then earlier on they told us that QB equals 5 times the length of BC. So I'm going to swap QB to 5 BC. Just like that, I'll swap QB to 5 BC because they are equivalent. They did tell us that in the question. And 5 BC plus BC, if there's no number in front here, it's a 1. And 5 BC plus 1 BC is 6 BC. And then finally, the BCs will cancel over here. And if everything from the top cancels, there's a 1 left over. So from this whole ordeal, we've got a 1 over 6 left over. And now we've finished up with this nasty barked down prawn of a question. We've successfully proved CT over PC is 1 over 6. CT over PC equals 1 over 6. Let's have a look where our 3 marks come from. So your first mark comes from the correct statement. The second mark comes from the correct reason of line parallel to one side of triangle. And the third mark comes from the correct expression for QC. So changing QC to 6BC. So it's quite easy to do these visually, but you've got to get used to how to write up this whole story. And that wraps up the first question in question 10. Question 10.2 asks us to prove that triangle QAC is similar to triangle QBD. Okay, geez, like fine, I will, dude. A please would be nice over there. Okay, let's get those triangles highlighted. Yes, that's so much better, bro. Okay, QAC is the orange triangle. QBD is the purple triangle. Now we are going to do this with angle, angle, angle. That's always the easiest thing to do to prove similar triangles. So I can see these two have an angle in common over there. They share the angle Q. So that's going to be my first angle. And I just write that down like this, AQB. So there's quite a few angles at Q. There's this angle here. There's this angle here. And then there's the whole of Q. So I've got to be very specific as to which angle I'm talking about. So I just say AQB. I follow the 3 letters around that angle. And I say AQB equals AQB because they are common. It's a common angle. Now we need to find another angle that's the same in both of these triangles. And now I'm seeing a circle here. And I'm seeing a bow tie, my bro. Angles in the same segment. Okay, so just a quick reminder of that. If you have angles in the same segment of the circle, then we know that they are equal to each other. Our one doesn't quite look like this. Ours looks more like this. If I just rotate that, then we get like a sideways bow tie. And this is the bow tie that I am referring to. Let me just highlight it so you can see it a bit better. Yes, the bow tie, so formal, bro. Okay, so with that bow tie, we're going to conclude that angle D is equal to angle C. And we're going to write that up just like this. Angle D equals C, angles in the same seg. I don't need to say like ADB because this is the only angle present at D. So if I just say D, there's only one possible thing I can mean, and the same applies to C. And then the third angle will always be equal by default. So the third angle inside of the orange triangle is this big one over here. And just to name that angle, it's going to be QAC. You can also say QAT if you'd like, it means the same thing. And then the third angle inside the purple triangle, we've got this one, so here's the third angle inside the purple triangle. And remember, the third angle will always be equal by default because of interior angles of triangle. And then just how I named this one over here, you follow the letters, so it's QBD. Alternatively, you can use B2. Also for this one, I could have used A1 because I have named it. But these are also acceptable. And now I'm going to copy paste this statement. Triangle QAC is similar to triangle QBD. And my reason for knowing that is I proved all the angles are the same. So angle, angle, angle. And now we have successfully done what they asked. Let's have a look where the 4 marks come from here. First mark comes from the correct statement with a common angle. Second mark comes from stating that D equals C. Third mark comes from the reason associated with that statement. And the 4th mark comes from your wee little reason over here. The last question in question 10 asks us to prove that QD times QA equals 30 BC squared. Okay, so we're going to look at the previous 2 questions to help us. So from the previous question, I'm going to extract ratios out of this using the smiley face method. So I'm going to grab this quickly. And after I grab that, I'm going to draw a little smiley face over both of them. Then I'm going to analyze what's here, and then that's going to help me choose the 2 relevant ratios I want. So I want a QD. I see QDs over here. So I'm going to have the smile over the smile over here. So I'm going to have QC over QD. And I also want a QA in the mix, and I see a QA over here. So I'm going to have the left eyebrow over the left eyebrow. So I'm going to have QA over QB. And we write it just like this. This is our statement. We know that these ratios are equal because the triangles are similar. I normally do these smiley faces in pencil and then erase them once I'm done extracting what I need. Okay, and I'm going to look at this, and I'm going to look at this. I'm going to analyze what I want and what I want to get rid of. So I want QA in the mix, and I want QD in the mix, but I don't want QC and I don't want QB. So I'm going to start to look at these and how I can get rid of them. So let's start off with QC. QC is this long side over here. And if you remember back to 10.1, we actually did change QC. So we changed QC to 6 times the length of BC. So we can hit that change once again. Okay, so after we made that change, we're getting one step closer. We've got 3 things we need. We've got BC now over there. We've got QD over there. And sorry, the tick should be there like QA. So we've got QA, but now this QB needs to go. He's a bit of a rotten egg. He needs to varm, bro. So let's have a look what we can do with QB. QB is over here, and earlier on they did give us this statement over here. QB equals 5 times the length of BC. So we can change QB to 5 times BC. So let's go ahead and change QB to 5 BC. And now I've got the right sides over here. So when all the ticks have been done, I'm going to cross multiply. So I'm going to bring this up to that side, and I'm going to bring this up to that side. And when I bring them up, I multiply. Okay, let's start by bringing that QD up. That's just going to give me QA times QD. Once that's out the way, I'm going to bring this 5 BC up. So I'm going to multiply the numbers separately. So 5 times 6, take a gander as to what it's going to give us. Dirty, my bro. And then I do the sides separately. So BC times BC gives us BC squared. And now we're done. We've successfully proved what they asked. So we can swap the order around to match this if you want to be comfortable. So I can switch the order of these two around because the order of multiplication doesn't matter. 3 times 4 is 12. 4 times 3 is 12. So you get the same outcome no matter which order you multiply them in. And then I just move this BC, 30 BC squared over to the other side of the equation. And yeah, we are officially done. Let's have a look where our 3 marks come from. The first mark comes from extracting the ratios from our similar triangles. The second mark comes from the raison for the similar triangles. And the third mark comes from multiplying this 5 BC by the 6 BC to get 30 BC squared. And also, I want to bring something to your attention. Instead of writing this, I can write this. Similar triangles. But I prefer the previous one because it's more specific. And yeah, it leaves no wiggle room for them to mark you down. And that will wrap up Vraagstel 10 of your paper, but